One of the types of angles studied in geometry is the right angle. We can classify angles based on their measures in degrees. The right angle always has a measure of 90 degrees. A small square inside the angle indicates a right angle. All right triangles have one 90-degree angle. Since the sum of the measures of the angles in a triangle is 180 degrees, the other two angles each measure less than 90 degrees and are called acute angles. The sum of the two acute angles equals 90 degrees. Again, look at the right triangle. This triangle's vertices, or the points where the sides intersect, are labeled as capital A, B, and C. Note that angle C is the 90-degree angle. The sides of the triangle are labeled based on the label of the vertex opposite them. Side A is opposite vertex A, and side B is opposite vertex B. Sides A and B, the shorter sides of the triangle, are called legs. Side C is opposite vertex C, the right angle. Side C is the longest side of the triangle and is called the hypotenuse. Pythagoras proved that the sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse. In other words, A squared plus B squared equals C squared. You can also think of it as leg squared plus leg squared equals hypotenuse squared. Notice that we indicate squared by showing a little 2. That little 2 indicates that we are multiplying a number by itself. We call this relationship the Pythagorean Theorem in honor of Pythagoras. Now let us look at the meaning of the theorem. If we draw a square so each side of it is the same length as side A of the right triangle, it would look like this. The area of the square is A times A, or A squared. Let us continue by drawing a square with sides the length of side B of the triangle, and one with sides the length of side C. Do not forget that side C is the hypotenuse. The areas of these two squares are B squared and C squared. Let us create a pattern with our squares. We will place one B squared against each side of A squared, so A squared is surrounded on all sides. Then we will repeat the pattern until it looks a little bit like a checkerboard. This is a tessellation. Now let us bring back C squared, which is the length of the hypotenuse squared. No matter how we place C squared on the tessellation, we can see the relationship between the three squares. Remember that the parts of A squared are yellow, the parts of B squared are blue. If we rearrange the yellow portions of C squared, we can reconstruct A squared completely. By rearranging the blue portions of C squared, we can reform B squared. A squared plus B squared equals C squared. Let us look at the theorem in a slightly different way. This right triangle has the length of its sides noted. Side A is 3 units, side B is 4 units, and side C is 5 units. We will represent 1 unit with a small square, called 1 square unit. To represent the square of side A, we will draw a square that is 3 square units by 3 square units. Side A squared includes a total of 9 square units. The square of side B is 4 by 4, totaling 16 square units. The length of the hypotenuse squared is 5 by 5, or 25 square units. If we add the area of A squared, or 9 square units, and the area of B squared, which is 16 square units, the sum equals the area of C squared, or 25 square units. But what if the lengths of the sides of the right triangle were 6 units, 8 units, and 10 units, instead of 3, 4, and 5? Would the relationship remain the same? 6 squared equals 36. 8 squared equals 64. If we add 36 and 64, the sum is 100, which is the same as 10 squared, the square of the length of the hypotenuse. The relationship remains the same.